let us find the direction of magnetic field at P due to wire A and B. So we will use the right hand thumb rule. So current in A, I1 is in this direction. So my fingers at P is going into the whiteboard. So here the magnetic field due to A at this point will be into the plane of this whiteboard. So let me see what will be the direction of magnetic field due to board. It's curling in this direction, which means it's coming out of the plane. So magnetic field at the point P due to B, I will express it as BB, is coming out. Are they in the same direction? No, they are in opposite direction. So we will find the magnetic field due to both of these wires, and the net magnetic field at point P, we will obtain that by subtracting them because they are in opposite directions. So case 1, let me first find the value of magnetic field due to the current in A, BA. What is the magnetic field at a point at a particular distance from a straight current carrying wire? It's mu naught I by 2 pi A. So what is mu naught? It's 4 pi into 10 raised to minus 7 times, what is the current in A? 12. Divided by 2 pi, and what is the distance of the point P from this wire? We saw this total distance is 5 centimeters, so this distance should be half of that. That is 2.5 centimeter. Now we have to express here the value in meters. So 2.5 centimeter will be equal to 0.025 meters. So you have to put here instead of A 0.025 and you will get a value. What is the value? Let me check. It is equal to 9.6 into 10 raised to minus 5 Tesla. So 9.6 into 10 raised to minus 5 Tesla. You have to do the calculation yourself using a calculator. So this is the magnetic field due to A. Now the magnetic field at P due to B is equal to, so the same formula, mu naught I by 2 pi A is equal to mu naught is same, but the current is different, right? Here through B the current is 15 ampere, so they expressed it as I1 and here I2. So it's equal to 15 ampere divided by 2 pi times the distance from B to P also is 2.5 centimeter. So I'll be using 0.025, and what is the answer? It's 12 into 10 raised to minus 5. So 12 times 10 raised to minus 5 Tesla. So the net magnetic field at P is equal to, we have to take the difference. So what is the difference? 12, 10 raised to minus 5 can be kept common, minus 9.6 into 10 raised to minus 5 Tesla. This is equal to 12 minus 9.6. So it is 2.4 times 10 raised to minus 5 Tesla. And what is the direction of this magnetic field? Which is more, magnetic field due to A or B? B is more. And B is directed out of the whiteboard or out of the paper in your case if you are doing it in a paper. So the magnetic field at P is 2.4 into 10 raised to minus 5 outwards or out of the paper. Out of the paper. Got it? Now let us see case 2. What is the case 2? If the direction of current through wire B is reverse, So here I am changing for case 2, the direction of current is, what was the direction earlier, downwards or upwards? It was in the same direction, no. Also here now the direction will be changed, it will be downwards. So here we got it as I2 in this direction. Direction of current in B is reverse. So let us see what will be the direction of magnetic field. That due to A will remain the same because we didn't change the direction of current. Let it be like that. But for B, we have changed the direction. So again, I'll be using my right hand thumb rule and hold this downwards. So my fingers are now pointed into the whiteboard. So here I have the magnetic field due to the current carrying wire B is directed inwards. So what should I do? Both the magnetic fields are in the same direction. So the net magnetic field at P, I don't have to find it again because their magnitude will be same. The value of current is not changed, only direction is changed. So only the direction of this magnetic field will change. So the net magnetic field at P will be equal to, I have to add these two quantities. So instead of minus 12 plus 9.6, because they are in same direction, into 10 raised to minus 5 Tesla. What is 12 plus 9.6? It's 21.6 into 10 raised to minus 5 Tesla. And what is the direction? Is it out of the paper? No, it will be into the paper. So let me see the question again. If the direction of current through wire B is reverse, then will the magnetic field B at P change? Yes, the magnetic field at P will change. That is the answer. It will change. And you can show here, one, in first case it's out of the paper, second case into the paper, and their magnitudes are also different. So I hope this problem is clear to you. So let's move to the next problem. So let's see the new question. The magnetic field produced by a 2-meter long straight wire carrying 4 ampere current through it at a point 0.16 meter away from the wire is less than the magnetic field at the center of the coil made from this straight wire. Again, if a coil of 10 turns is made winding the straight wire, then the magnetic field at its center will be 100 times greater than the coil of 1 turn. Now A, what is the magnitude of magnetic field at a point 0.16 meter away from the wire? So first question A is straightforward, but this term is a little twisted. You have to imagine that situation. So let us first solve this A part. What is the magnitude of magnetic field at a point 0.16 meter away from the wire? So a magnetic field produced by a 2-meter long straight wire carrying current 4 ampere. So the length of the wire is given, current is given. We have to find the magnetic field at a point 0.1 meter away from the wire. We know that the magnetic field due to a straight current carrying wire B is equal to mu naught I by 2 pi A. So you can directly substitute the values. Mu naught is 4 pi into 10 raised to minus 7 times current is 4 ampere divided by 2 pi times what is A? A is the distance from the wire, that is 0.16. So you can substitute these values and you will directly get the answer in Tesla. It's 5 into 10 raised to minus 6 Tesla. So 5 times 10 raised to minus 6. So this was a straightforward question. We got the value. Now, verify the statements of this term. This is the step. So let us see what each statement is. So the magnetic field produced by a 2 meter long straight wire carrying 4 ampere current through it at a point 0.16 meter away from the wire is less than. So what we found is less than the magnetic field at the center of the coil, which means we are making it round, coil made from this straight wire. Okay, they did not tell us what is the radius of the coil, nothing about the coil. But this wire is wound into a coil, one single coil. And they have given the length of the wire. So, if a 2 meter wire is wound into one coil, so the length of the wire will be the circumference of the coil. So, here for B, what are they doing? They have wound this 2 meter length into a coil. And we have to find the magnetic field at the center of this wire. So, a straight wire wound into a coil. So, what is the length of this coil? It will be the circumference of the circle. Suppose R is the radius of this coil after winding. The circumference of this coil will be the length of the wire. So, I can write 2 pi R is equal to 2 meters. That is the length of the coil. So 2 pi R is equal to 2. So what will be R? R will be is equal to 2 divided by 2 pi. So for R, I can put the value R is equal to 2 divided by 2 pi and substitute in the value of magnetic field due to a current carrying coil at the center of the coil. So what is the magnetic field due to a circular current carrying wire? We have learned that formula. It's equal to mu naught I by 2R, where I is the current, R is the radius of the coil. So this is equal to mu naught, we know, 4 pi times 10 raised to minus 7. And what is I? 4 ampere divided by 2 times 2 by 2 pi. So 2 pi will be going up. So 2 by 2 pi. So you have to find the value. And the statement is that this will be, okay, this, if it is straight, will be less than what we get here. Let us see what we get here. Okay, we got it as 7.85 into 10 raised to minus 6. 7.85 into 10 raised to minus 6 Tesla. So which one is less? This one. So this first statement is hence verified. So here, if I represent this as B and this as B1, then I will get, let me represent this as R1, and then we know that B1 is greater than B from these two values. This is 5, this is 7.8. So B1 is greater than B, or B is less than B1, and hence the first statement is justified. So the magnetic field produced by a 2 meter long straight wire carrying 4 ampere current through it at a point 0.16 meter away from the wire is less than the magnetic field at the center of the coil made from the straight wire. So this we have verified. Now, what is the second statement? Again, if a coil of 10 turns is made winding this straight wire, then the magnetic field at its center will be 100 times greater than the coil of 1 turn. So, we don't know this A part now. We need only the magnetic field at the center of the coil we need. Again, this wire is taken and it is wound how many times? 10 times. So we get 10 turns with the same length of wire. What is the length of wire? 2 meter. Now it is wound into 10 turns. So each coil will have a circumference 2 pi r and the total length is 10 times 2 pi r. So let me rub this part because it is wound into 10 turns, right? So I am continuing this. So after here, I want this value. Let it stay there. So I will not rub this because we will have to compare the value. So this value, we know this is for one turn. Now let us find for 10 turns. So for 10 turns, I will express it as B2. So R will be expressed as R2. So now 10 times 2 pi R2. When you make it into smaller turns, we know that the radius will also become smaller, right? One single coil straightened and made into 10 turns. So the radius will reduce. It will be a different value. That's why I am expressing it as R2. So 10 times 2 pi R2 is equal to 2 meters. So I have 10 pi 2 pi R2 is value 2. So R2 will be equal to 2 divided by 10 times 2 pi. Now again, in order to find the magnetic field, there are 10 turns. So to find the magnetic field at the center of that wire, we know B2 is equal to mu naught I by 2R if it was one turn. Here there are 10 turns. So mu naught Ni by 2R2. Current is not changing. If there are n turns, you have to write it as Ni. So this is equal to, where n is the number of turns, 4 pi times 10 raised to minus 7 times 10 times current is 4 ampere divided by 2 times, what is our 2? 2 by 10 into 2 pi. So 2 times divided by, so goes up 10 into 2 pi. So what is the value? We'll get the value as, okay, 7.85 into 10 raised to minus 4 Tesla. See, 7.85 into 10 raised to minus 4. Here, for one turn, it was 10 raised to minus 6 Tesla. So we know that 10 raised to minus 6 into 100 will give you 10 raised to minus 4. So we got that B1 into 100 will give you B2. So this value 10 raised to minus 6 into 100. 100 means 10 raised to 2. So you will get 10 raised to minus 4. So you have B1 into 100 will give you B2. So the second statement is also verified. So both statements are verified. Is that clear to you? If not, let me know that through the comments. So now we have one more problem to solve. So this is our last problem. In the figure, so this is the figure. In the figure for current I1, the magnitude of magnetic field at point K, this is point K, is 8 Newton per ampere per meter. Newton per ampere per meter, same as Tesla. So it's 8 Tesla here at K. Agree? A. Find the distance D, this distance D, of the point K from the conductor AB. So, the magnetic field at this point K is given. We know the current I1 is 2 ampere. And we have to find now the distance between the point K and this current carrying wire. So, which equation we will use? We know the magnetic field due to a current carrying wire at a distance, right? So let us use that equation to find the value. So B, the magnetic field due to a straight wire carrying current, is equal to mu naught I by 2 pi A. This is the equation we learned. And mu naught, we know it is 4 pi into 10 raised to minus 7 times, what is the current here? I1. So it's 2 ampere. 2 divided by 2 pi into A. A is this distance from the current carrying wire. So I can put instead of A, B. And they have also given the value of B. So I want to find D here. So what should I do? I should take D to this side and B will go down. So I am taking D here and B will come here and B's value is given. So I can directly substitute. So D is equal to, I am keeping all the rest same. Okay, I can cancel this pi and this 2, right? So what is remaining here? 4 into 10 raised to minus 7 divided by, instead of D, B will come. What is B? 8. So let me put 8 here. So this is equal to 4 by 8, 0.5 into 10 raised to minus 7 meters. So we found D. That was straightforward. Now let us find what is the next question. Analyze what will be the magnitude and direction of the resultant magnetic field at point L. L is in between these two wires if the direction of I1 is reversed. So what will be the magnitude and direction of the resultant B at point L if the direction of I1 is reversed? So what should I do? I have to reverse the direction of current. So instead of I1 in this direction, I am going to put I1 in this direction. I have to find the resultant magnitude at a magnetic field at L. So magnetic field at L will be both due to the wire AB and due to the wire CD. So first of all, since magnetic field is a vector, we have to find the direction of magnetic field due to both of these wires. If they are in the same direction, we will add them to find the resultant magnitude. If they are in opposite direction, we will subtract them to find the resultant magnitude. So how can we find the direction of magnetic field? Again, right hand, and the thumb directs in the direction of current. So it's like this. So up it will be going into the plane and down it's coming out. So here at L, my fingers are coming out. So I will express here the magnetic field due to AB. It's due to current I1. So I can represent it as B1. So B1 is coming out. So once I reverse the current. So here at L, B1 is coming out. Okay. Now let me find what will be the magnetic field due to CD. So due to CD. So again I will take my right hand in the direction of current. Thumb is pointing in the direction of current. See, my fingers are coming out at L. So here again I have the magnetic field due to the second wire is also coming out. So what should I do? I have to find the magnitude at L and add them. So let us find here magnetic field B1. Magnetic field at the L. See, in the figure they have given this as D. This is also D. This is also D. So L is at a distance D from wire AB and also from wire CD, and we have found D in this question. So we can substitute for D 0.5 into 10 raised to minus 7 meters. So we have the magnitude of magnetic field B1 due to the current I1 in AB at the point L distant D from it as B1 is equal to mu naught I by 2 pi D. D is the distance. So this is equal to 4 pi into 10 raised to minus 7 times, what is the current I1? 2 ampere. 2 divided by 2 pi, what is the distance D? 0.5 into 10 raised to minus 7. So 2 pi gets cancelled. 10 raised to minus 7, 10 raised to minus 7 gets cancelled. 0.5 means 1 by 2. 2 will go up. So this is equal to 4 Tesla. 4 Tesla outwards. So let us find what is B2. B2 is equal to, say, mu naught, but I2 by 2 pi D. D is same. So here this is equal to 4 pi into 10 raised to minus 7 times 3 divided by 2 pi into 0.5 times 10 raised to minus 7. So 4 pi, 2 pi gets cancelled, 10 raised to minus 7, 10 raised to minus 7 gets cancelled. 0.5 means 1 by 2, so 2 goes up. 2 times 3, 6 Tesla. So we have to add them, they are in the same direction. So what is the resultant magnetic field? Resultant magnetic field B is equal to 4 plus 6, that is 10 Tesla. So that's it. We have solved 8 problems now. And if you have any doubt in any of the problems, please mention that in the comment. And thank you for watching to the end.